So you do this thing every day called breathing. But why do you do that? You breathe all day, every day, and even while you're sleeping, you're breathing. So your body seems to think it's pretty important. But what is it doing for you? The answer is in a process called cellular respiration, which is what we're going to talk about today. And essentially cellular respiration is turning glucose, which comes from food, and oxygen, which is what you breathe in, into carbon dioxide and water. Now, this process of cellular respiration all the while is creating energy that will later be stored in ATP, which we'll talk more in depth about the process of storing energy into ATP later, but all you need to know is that the process is creating energy and it's being stored into ATP. So we've got this equation in front of us, and it's all a bunch of words. We can't really see very clearly that the reactants on the left side is going to be equal to the products on the right side, and that they're going to be proportional. So I'm going to try to convince you that there's going to be just as many atoms on the left side as there will be on the right side. So let's look deeper into this equation here. Glucose is made up of 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. Oxygen is just made out of 2 oxygen atoms. Carbon dioxide is made up of 1 carbon atom and 2 oxygen atoms. And water, you've probably heard this before, that water is H2O. That means it has 2 hydrogen atoms and 1 oxygen atom. Now you may notice, those of you that are really smart may have noticed that these aren't equal to each other. There are a lot more oxygen atoms, for instance, on the left side than there are on the right side. So we have to add further notation. We add a 6 in front of the O2, a 6 in front of the CO2, and a 6 in front of the H2O. So that makes it so that the total number of oxygen atoms on the left side is going to be equal to the total number of oxygen atoms on the right side, and likewise for the carbon atoms and the hydrogen atoms. You can see in glucose alone there are 6 carbon atoms, and now that we have the 6 in front of the CO2, there are also 6 carbon atoms on the right side as well. Let's draw out each individual atom. We have 6 carbon atoms in a glucose molecule. We have 12 hydrogen atoms in a glucose molecule, and we have 6 oxygen atoms in a glucose molecule. And they're all binded together, they're all bundled up. Then for the O2, we have 2 oxygen atoms for each one, but since we added that 6 in front of there, we have 6 of these individual O2 molecules. Now usually these are all binded and bundled up together and disorganized, but for this illustration we're going to organize them. So you can see here that there's 12 hydrogen, 6 oxygen, and 6 carbon. Now we're going to see each of these atoms binding together to make the products. Starting with the carbon atoms, we'll send the carbon atoms each with an O2 molecule to the other side, and you see that they're making CO2, 1 carbon, 2 oxygen, and conveniently there's 6 of them. Look at that. Now the hydrogen and the oxygens left over from the glucose molecule, they're going to leave as well. So 2 hydrogen are going to pair with each 1 oxygen, and they're going to go to the other side as well, making 6 H2O molecules. Now I'm going to show you that this also works in reverse. Each of these carbon atoms can go to the other side, followed by the O2. And then the water molecules can meet the carbon atoms, and they can all bind together to make glucose again. Now this process of going back and forth is creating energy. And if you remember me saying from earlier, energy is the most important thing that cellular respiration does for the body, both humans and all other living organisms that cellular respiration happens in. And if you remember me saying, it's going to be stored as ATP. So why am I explaining this to you in this way? You can see that there are just as many elements coming in as coming out. And similarly, the amount of energy that you need is going to require a certain amount of oxygen and glucose in order to produce that energy. And I'm about to show you 2 clear examples as to how you can see in everyday life that oxygen in particular, we're not going to go as into depth about glucose, but oxygen in particular is needed to produce energy, and you can see evidence of this in everyday life. So let's look at the first example. Let's say I'm hanging out on my front porch, and I'm grading all the A+ papers that appear on my desk every week. And I'm breathing quite calmly because I'm relaxing on my porch. I'm not using much energy because A+ papers are easy to grade. When I start hearing some music, it sounds like the ice cream truck. So let's say as soon as I realize that it's the ice cream truck, I sit up, I toss my A+ papers, and I sprint as fast as I can and scream ice cream. And I'm running as fast as I can. I'm using more and more and more energy because I want to get to that ice cream truck as fast as I can. And all the while, I'm breathing more heavily. The faster that I run, the more oxygen I breathe in and CO2 I'm breathing out. So let's say that I finally get to the music that I'm hearing, and I see that it's a frozen yogurt truck. So I stop, I look very sad, and I turn around. Because I thought it was ice cream, but it's actually just frozen yogurt. Now that I've stopped and I've turned around, I'm using a lot less energy, I'm going a lot slower, and my breathing slowly goes back to normal. A normal amount of oxygen I'm breathing in, and a normal amount of CO2 I'm breathing out. So my question to you is, why did I breathe heavier as I ran faster? And similarly, why did my breath return to normal after I found out it was a frozen yogurt truck and I stopped and turned around? If you answered that the faster I ran, it required more energy, and the more energy I needed required more oxygen to produce that energy, then you are correct. Now we know the more energy we need to make, the more oxygen we need to make that energy. But what if you want to use as little oxygen as possible? In this situation, we're going to use you as an example. This is you. And you have a friend. You guys went to the pool. And then your friend, who who is not in biology class challenges you and says, I bet I can hold my breath longer than you can. So you guys dive into the depths of the pool. Once you get to the bottom, you find out that you have two very different strategies. You hold on to a grate at the bottom, and you try to conserve your energy and use as little energy as possible, while your friend is struggling to stay underwater and squirming about and flailing his arms. Who do you think is going to win this breath-holding contest? If you answered that you win, you are correct. Now the question is, why did you win? If you answered that you did not need as much oxygen because you were not making as much energy, you are correct. Since you used as little energy as possible, you did not need as much oxygen to make that energy, and you did not make as much CO2 to be released. See, biology makes you a winner. You won because you knew about cellular respiration, the process of turning glucose from food and oxygen into carbon dioxide, water, and most importantly, energy. You knew that in cellular respiration, the things that come in, glucose and oxygen, is proportional to the stuff that comes out, CO2, H2O, and energy. You are a pretty smart person. Who's your teacher?